understanding, if the nanos are preloaded, why isn't the reaction proceeding immediately? Once the nanomaterial is created.
You mean why doesn't it work without an applied voltage?
Earlier experiments, electrochemical experiments, there was a big emphasis saying that you need to do cathode to be loaded. So in Poland, Baranowski loaded a cathode to 1.06, and it just sat there not doing anything. And so we've actually been aware that loading by itself is insufficient. And it was noted in SRI experiments that if there's a deuterium flux, that can stimulate an excess heat event. So last week I spoke about results showing flux in, flux out relation of energy and flux. In essence, the picture is you got to assemble your, if you're thinking about a laser type analogy, you got to produce some gain, you got to assemble everything so it's ready to work. But unless you stimulate it, it's happy as a clam just sitting there. My view is that Mitchell's current is actually providing the stimulation. In this case, electrical current, in my view, is causing phonon excitation, terahertz phonon excitation, and that's where that energy is going into. And without having excitation there, there's no. All of my models say you have to have monotone excited before any of the processes go on. So
are there any, just my ignorance, but I'm not aware of anything I've ever seen in the literature that suggests you can excite phonons with a DC current.
how about most of the literature on electron phonon coupling? In the electrochemical experiments, not only is there direct electron phonon coupling to potentially all phonon modes, and some of them are high frequency modes, but as pointed out by Fleischmann by CCF4, there's an effect where if you get electrical current flowing in a hydride or a deuteride, the hydrogen and deuterium moves in the opposite direction from the electrons, and in doing so, provides direct excitation of optical phonons.
There was a corollary. We ought to get a terahertz radiator, because that would test your hypothesis.
But the headache with that is that at some point we're going to have a list of so many homework projects for you to do.
Look at all the people we got. All we need is more. Would somebody put some skin in the game, make more nanors? The nanor that we showed, the Series 6 nanor, as I'll show you in a bit, at the MIT demo, during the demonstration of Peter's course, showed an energy gain of 14 times input. And for the next few days, it went up to 16. We actually went up much higher. And we'll be reporting that if the paper gets accepted at ICCF 18. Series 5 nanors. Okay, here's one of them. Now again, this is, I think these are more advanced. These have the proprietary method of loading. Not as good as the 6. Because again, each of these we're learning a lot. But I'm going to try and show you to improve your pattern recognition so you can recognize in a control system when we get the excess energy. So here we are looking at counts. This goes up to about 900. Each one is 7 seconds. And remember, you got to multiply those two for the total time. Again, I apologize for that. Here's our power in and power out. And we're going from about 10 milliwatts up to 100 milliwatts. And here is our input to the ohmic control. And on this side is the delta T normalized. Is this one normalized?
Yes.
Yeah, this input power normalized delta T. So we'll be able to take the ratio of this to get the energy gain. Yeah.
So, Mitchell, if you were in a long time, for your control at the different power levels, you would have a flat line because in principle, you know, the ohmic control gets temperature rise proportional to the input power. Your curves are not, and your curves are not. Here is a direct result that you're really not running the signal long enough to
Correct.
get to equal.
Not in this run. But remember, what we're doing here is one, I'm trying to find out if it's active. Okay, this was 5.0. This was Series 5, the second one we did. And I think also I was in a race to get to the demo, because here we're running, what a waste of January 1st. I should have been on celebrating getting drunk. But anyway, working in the lab, here's the ohmic control, here's the output, input power normalized. And here is to the NANR device. And so we want to compare, let's say, here to here. We take that rate. Neither one has reached equilibrium. But again, what I'm trying to do is learn to see if there's a response. Two, to determine an optimal operating point, just to sort of tune in a little bit. Yeah.
So if you look at the ratio of the red line on the right versus the red line on the left, the idea here is that you're seeing something in general neighborhood of a factor of what, like 5.
5 to 7, yeah.
Gain.
Yeah, which at the time was pretty good. It was higher than Series 3, not as good as Series 6, where now we're happy. I mean, I'm not happy now unless I see an energy gain of 15 to 40, but that's later. Yeah.
On the ohmic control, you put in that step, say the first step of power input.
And I didn't wait for equilibrium.
But the heat is going down, even though there's a continuous input.
No, it isn't. This curve is input power normalized. So as soon as we switch the input power, we're dividing by this. Whatever the delta T is, the delta T is relatively continuous.
I got it.
But we're dividing by the input power, which rises, so it's going to come to half the amount.
Right.
Okay. Let's see, this one I believe is heat flow. Remember, what we do here is we do multiple ways of looking at the energy gain. So that was the delta T, and then we made an adiabatic. We took fire bricks all the way around, except for one area where I controlled where the heat would leave. And there we put one of these miscalibrated heat flow sensors. So here, for example, we're looking, these red curves are heat flow. Okay? And I believe this is also input power normalized, so we can take the ratio. So this is a calibration pulse. All of these have calibration pulses in the beginning. That allows me to calibrate the A to D equipment. So you'll see these in a lot. So we get calibration, ohmic control, here's the NANR, another calibration, ohmic control, NANR. And what we find is that for less input, half the input, we get about 3 times more out heat flow. So these two curves for the NANR 5-02s, an even different one from the last one, gave us excess energy reproducibly at different levels of drive, and we were able to show it both by delta T and by heat flow. And here's by calorimetry, the third way, which is we took all of the things I showed you yesterday, where we do thermal waveform reconstruction, we put in our calibrations, we convert the power. So here is our ohmic control, and it's our power in. Here's our power out from the ohmic control. Here's our power into the NANR. Look at that sweet power out from the ohmic control. You see a little step function when we do our calibration here again. So this is actually reproducible. We're getting a little bit more out here. And if we integrate the curves, we get these, I'm sorry they're a little bit light, these dotted curves that you read off the right line. And the right vertical axis is energy. And so this difference is our excess energy over here. And that's something like 400 joules that we did over 17. So we multiply the two. It's 1,700 times 7 seconds is the total amount of time. Okay. Looking at the electrical resistance, our ohmic control does what we would expect an ohmic control to do. It's constant. No surprise there. But as usual, the nanors are nothing but trouble. And here the nanor goes from, I think it's 12, I think this is in kiloohms. So here this is 1.2 megohms, and it comes down to 200 kiloohms. Tough thing to work with. But if you deal with it and have that Nanor Explorer to run it, we're able to get the excess energy out. Any questions? It's just more of the same. Here we did another one. I wanted to do a few before I brought it into the demo. I have a little performance anxiety, so I wanted to make sure we had several. So here was our 503. Here's our ohmic control. Again, what we see, this is relative input power. We put in this, we get this out of the ohmic control. We put this into the nanor, and bing, we're getting more out. And this is heat flow too. We see it with this is run B. This is also run B. So we see. Sorry about that. So basically, here we see excess energy by heat flow. Since it's input power normalized, we can take the ratio. We're getting a little bit higher energy gain here. And we can also see it with, this is input power normalized delta T. We can take this ratio. And here it's getting closer to equilibrium because we're only doing one level. Now we know where we want to drive it, and I'm willing to let it go longer to get the energy. And we can see that the nanor is deteriorating a little bit here. We're probably driving off the deuterium or something. In the early ones, we didn't glue it very well. It wasn't until 6 that we really learned how to do it. Yeah?
Did the size of the nanomaterials make a difference, or did you try different size particles?
Oh, it makes a big difference.
And how did you zero in on the right size, and what size is that?
We're doing it at Edisonian right now. It's just, I wish there was more engineering. There's just, everything is a question of what to do. So you're just watching me plot along. I'm just sharing. In fact, I'm trying to share with you the plotting as we did it rather than just show you the final result, which is probably what I should have done. This is actually, it turns out that we learned a lot about even from the calibration pulses, but I don't want to get into that now. Series 5, by the time we made the 23rd one, here's our ohmic control. That's a little bit closer to equilibrium, isn't it, Peter? Okay. And here, and this is, again, this is 2,000, so it's 14,000 seconds. So we're up about a seventh of a day. And here we drive it at 3 levels. And the ratio of these two, we're looking at input power here. That's our output power. And by doing the fact that it's input power normalized, we can take the ratios. We can see that at this drive level, the ratio is this much. We go higher, it's this much. We're almost seeing the optimal operating points come out again. That if we want to do the max of gain, we do this. If we want to maximize the motor, as I showed you yesterday, that's a different issue. And there may be 2 optimal operating points, one for gain and one for actually driving a device. Okay, here's a delta T. It's more of the same. That we were just, again, here's another one where we're looking at input power between 10 milliwatts and this is a tenth of a watt. By the way, there's a lot of talk about the fact that it's low power. We do low power for a number of reasons. One, these devices have under 100 milligrams of material. These aren't pounds of material. The nanor that we showed at the open demo at MIT had 35 milligrams in it of active material. That's all it was in there. Okay? So we do it for 1, safety, 2, because we want a fast response time. I mean, when I showed you the Fusor data yesterday, I showed you, for example, that we did an ohmic control over a day. We would then do a run over a day. And you're not going to get much knowledge that way. With the nanors, by driving them at low power, I can get a turnaround where I can do 10, 20 experiments a day. And for us, that makes a big difference. The evolution of understanding is speeded up. Okay? So here, we're looking at full-bore calorimetry. And with the NANR here, this is 523A. This is our input. Here's our outputs. It's pretty much at equilibrium. We've learned how to do that by now, not like in the initial ones. And here's our NANR. So this is our excess energy is here, and our energy gain is, our power gain is here, and integrated over will give us our energy gain. Here's a different run. It's just more. But again, you can see that here we're getting less out than we put in. Here we're driving a little higher. We're starting off at a 1/10 of a watt input power. We're not quite capturing it all. But with the NANR, we're getting more out than we put in. So we put less in, more out. And we're back to the control, and we see it's reproducible. Here again, we see that when we look at energy, they're linear, they overlap, whereas with a cold fusion device, it's superlinear because we're getting more energy out, okay? Here we see the heat flow. This also shows excess energy. I don't think this is input power normalized, so you really can't compare it. But here is to the control, heat flow out, same input power to the NANR, much more heat flow out. So we see, in fact, there is a verification of excess energy. It's indisputable. And we see it for multiple input powers. We see it for multiple devices. We see it's reproducible. And we see, in fact, we have separated the loading from the activation. We can take these devices as dry. We're up to near Christmas. I'm almost ready to have the nerve to come to a demo, but not quite. Let's see. So a little bit more material. Okay. Let's do Series 6. Any questions?
So Mitchell, you went through a similar exercise before this class, and the nerve didn't make it for a demo to be here this time?
Oh, no.
I'm clowning, of course.
No, I should answer that question. Why there is no demo here? We are using the NANRs in experiments at the moment. One experiment we're doing is an autonomous run where we are looking for the emission of ionizing penetrating radiation. That is, are we getting gamma rays out? In order to do that, most of the background that you are exposed to during the year are your neighbors, yourself. The potassium-40 in your body is causing most of your background radiation. So we've built these devices to run autonomously. And in order to connect enough data, they're running. And so they're at work. That's why they didn't show up.
I wanted to briefly come back to the question of scale that you alluded to earlier. I think that's a natural question most people would ask, and you answered it already, but can you just reiterate again that you see no impediments to scaling up?
I don't. I mean, you could take N nanors is one way. And we're investigating ways of making bigger nanors. Our Series 7, I don't want to talk too much about it. They're just bigger. We're making them a little bit bigger. We're going in steps, just like we did here. So this is the demonstration nanor that we brought to MIT. And we took one of these preloaded devices, and this was actually the run during the course. I'll come back to it in a bit. And it gave incredible energy gain. And yippee-ki-yay, here's our control. We're looking at input power. This is time. From 0, the count goes to 4,000, a little over 4,000. Each one's 4 seconds, so this is 16,000 seconds. Input power goes up to 100 milliwatts. Again, one of the reasons I made these low power, one thing I left off is, in addition to fast turnaround time, I wanted to leave it here unattended. And when we did the demo in 2003, somebody actually, in Tuesday afternoon, disconnected the power supply. I kicked everybody out of the room at 4:30 because they disconnected our 600 power supply and connected it to a chair. And I don't know why they did it. They shouldn't have gone there. I mean, we spent a lot of effort to make sure nobody would get in there, and they did. It might have been the same person that stole Patterson's beads at that meeting. Yeah.
Mitchell, your power on the left is a power axis, and you had called it input power going up to 100 milliwatts. milliwatts. But if I look at the input power for the nano, it looks like your input power for the nano is going up to like 6.5
Oh, yeah.
milliwatts, and it's the output power. In this case,
That's
it's
right.
75 or 80, getting close to 80 milliwatts.
Now, I stand corrected. The axis goes to 100 milliwatts, but here is the input power to the control. Here is the input power to the nano. So when you read that off, as Peter says, we're talking only a very few milliwatts going in, but we're getting 70 milliwatts out for a tiny amount in. And when we integrate it, here's our energies. These two match, and this separation is our energy gain, and we ended up with an energy gain during the course of about 300 joules. And we'll come back to that in a second. Series 6 nanors. I'm just going to, we did a lot of them before we brought them here. Here, let's see, this one is, this is, again, we're not reaching equilibrium. I'm practicing before we bring it here. Let's just jump ahead. This is the date. We're almost getting ready for the course. So before the course, here's our calibration pulse. Here's the input to the control, not labeled, sorry, input to the cold fusion device. And we're getting, for this amount of input, this is our input normalized. I think this is not input normalized, right?
Correct.
This is just delta T. So you cannot take the ratio with this one, but I'll do that in a second. So if you want to measure the actual temperature, we put in this much to the ohmic control, we get this much temperature rise. We put in about half that much power to the nanor, and at equilibrium we're getting at a higher temperature. Yeah.
And John, one of your slides yesterday, you said that you're measuring temperatures accurate to between 0.6 and 1 degrees.
Better.
And if this is absolute delta, if this is delta T, and the numbers are pretty small, then you scratch your head. Do you want to talk a little bit about?
Yeah, that's the difference between accuracy and precision.
Yeah.
I think that we're dealing with thermocouples. You may not have the accuracy within a degree, but you certainly have the precision. So what I showed was the accuracy, but the precision's much
So,
less.
for example, you have relative numbers here. How accurate do you think your relative temperature measurements are?
I think they were talking hundredths of a degree. I think the reproducibility, which is what we mean by precision, is much, much finer than the accuracy.
Well, the question's a slightly different one. You're going from a relative temperature measurement, in a sense, to how much excess power. And so part of the issue is how should we trust it? And a reasonable answer is well, you're putting in calibration pulses, and the goodness of calibration pulses is a measure of how we should trust it. But
Good point. I'll have to add a temperature pulse now. It's a good idea. It's good, and we'll do that too. Very good question. Here we see the input normalized delta T. And here we can see that for different input powers, we are at equilibrium. Each of these counts is 7,000 seconds, so we go to 4,000, so we're at 21,000 seconds. So over here, the ohmic control, no matter how hard we drive it, the input power normalized delta T, with every precision it is, comes out with this number, and over here we get this. So it's this ratio is the excess energy. Yeah.
So if I try to read on the axis of this plot to try to make an S-to-S ratio, it looks something like a factor of 10 power gain here. Is that consistent with what you would
That's right.
conclude?
Actually, I think it's a little higher, because I think this is, yeah, it's very close. And we can actually determine it 2 ways to double check that. One by 3 ways. One by then looking at the heat flow, and 2 by looking at the calorimetry. For calorimetry, you can detect it by taking the ratio here of these two. But the other one, you do the ratio there. Here it's here. Here's the input power. Here's the output power. And I think that ratio also is about 10. So here we did the demo. These are the people who came to the course. And here's our floating. Again, it was inside because the wires were hanging, because I no longer could use the circuit boards, because the circuit boards were essentially shorting everything out at the time. And actually, the cold fusion device is in here. That's the calorimeter. And the whole drive circuit's here. And everybody was happy seeing the excess energy. This is what we got on the day of the open demo. This was LANR Series 6, number 33. These numbers just refer to processes that we do to it, so we can keep track of how we treated it, and that way we know that we either don't do that Edisonian-like or persist. And what we found, the heat flow detector was not working the day of the demo. It was that night. It kicked in, but it was not working because Peter's office was a little too hot. But by delta T over input power, we got a gain of 12.5 to 14, and that matched the calorimetry, and that was our excess energy of a run during a 2-hour course. And these were the actual data that then appeared on the internet. So here, we're looking at the run in seconds. So this is going from 4 seconds each count to 5,000. So this is 20,000 seconds. This is our control pulse. We didn't do temperature pulses. We've got to do that now, I guess. And here's our control. Here's the LANR. And this is just looking at delta T. This is not input power normalized, so this is not going to form a straight line. As we increase the power to the control, the delta T is going to keep rising. And the same thing for here. And when we do the delta T, normalized, ba-bing, voila, this becomes a flat line. And we can then compare our input power, which is a little noisy, the input power here, which is less noisy, to the output power. And we do this ratio to get the energy gain. Okay, questions?
Power gain.
Power gain, thank you. We have to do the integral of that to do the energy gain, yes. Here we get the energy gain by doing that. And again, we didn't have the heat flow yet. Here's the calorimetry, which I showed you before. Input to the control, output to the control. Input to the LANR, output to the LANR. This is our excess energy. Well, it turned out the evening after the demo, the heat flow sensor did kick in, as it did for the next 3 months, and we got lots of data. And we drove this at different levels. I tried to do experiments during this, so you're going to see that the energy gain goes up, it goes down, because we're actually running different experiments. We're driving it at different levels, and later on we were looking at the impact of different applied magnetic field intensities. Yes, Peter?
I apologize profusely, Mitchell, but on your last view graph, or set of view graphs here, one of the things that I was struck by during this experiment, that I was essentially flabbergasted by, was the ability to have a current controlling the excess power. In essence, the nanner sits there. You now apply current. It does its thing. You turn the current off, it turns off. I mean, in essence, this is a...
Not totally. There is some heat after death, but yes.
If you like, over the years, there was a big issue because early on, the excess power bursts would come at their own accord. That they would start and they would stop. And people would talk about the cold fusion fairy. In essence, a big advance that was made at SRI was the recognition that if you ramped your current up, that the current ramping could stimulate an excess heat burst, so you could turn it on. But on the other hand, even in those experiments, the excess heat would turn off when it wanted to, rather than when you would want it to. And I showed data for the single laser experiments, which were the first indication of systematic controllability. The laser would turn on, the excess heat could turn on, the laser would turn off, and the excess heat would turn on. I I showed that the two laser things, where the two lasers are coming on the excess heat response would be nice and clear. So that was a measure of controllability. But in essence, this current control that you have for this manner, in my view, is absolutely stunning. This is one of the things that's revolutionary about this manner from my perspective.
Is one possibility for this that we separated the loading from the activation, and that if you have the solution and you don't have it preloaded, now the question is, maybe the processes can either be a loading process or some of it may be leaking out versus activation. And there you can't control which of the two.
Having separated the loading from the operation, now when you operate it, this really brings out the connection between the current driving the excess power. You turn it on, your nanner goes on. You turn it off, the current off, your nanner turns off. And that's like really interesting.
We drove it that night after the demo. Here were the results from that evening. This goes up to 17,000 each, again, is 4 seconds. And we're looking here at input power and just delta T, again, so this won't be flat. Control, nanor, control, nanor, control, nanor. Usually we'll put a wide space in between, but for the demo, we left a lot of that out because we had already done that, and I was interested in getting the duty cycle up as much as I could. And one interesting thing here is you see that the peak excess energy is falling a little bit. So it's not totally reproducible in that we are changing the material as we drive it. It may be loss of fuel, it may be redistribution, maybe there are other changes that are occurring. Maybe we're driving off some of the fuel.
Are those changes reversible if you wait a while, or is that nanner done forever? Is that the
Without other things, it keeps coming down. We did make a big discovery where we were able to rejuvenate nanors. And that's a whole separate group of slides and information that I hope to release later this year. But we found a way of amplifying the effect, where cold fusion may only be the first stage. But this is a good first stage. Here again, what we see by the normalized delta T, now this becomes a flat line for the controls. Here again, we see there is a fall off, but our power gain is this ratio, this ratio, this ratio, this ratio, for different drive levels. So if you deconvolved it, you would see that there's an optimal operating point. And if somebody wants to sit there, I'll give you the data. You can give us the OOP as a function of time. As I showed you yesterday, we see that with optimal operating point manifolds. They change with time. Here's the heat flow. As I told you, mercifully, it kicked on that night, and we were able to finally measure an additional verification. So here's our heat flow normalized to input power. And we didn't quite hit equilibrium here. We did not hit equilibrium there. Here we sort of did. But our ratios are this to that, this to that, this to that. This is our power gain. And over the night, here was our calorimetry. Our input went to about 25 milliwatts input to the control, about 15 milliwatts to the nanor, and we're getting out 120 milliwatts by full calorimetry. And here is our excess energy over the evening. And again, notice we're getting a change of the nanor. It's not, it's a dynamic device. It is losing some of its power gain if we drive it the same way. And we kept going. This is the second day after the course. I can just keep running through. Here's the delta T. Here's the normalized delta T. There's our ratio. Here's the heat flow. And there's the calorimetry. So here's our power gain here versus the power gain this way. The important thing is the nanors demonstrate somewhat a linear time invariant response to the applied voltage, but not totally time invariant because there is a fall off. Peter?
So Mitchell, you showed that overnight that you got some substantial changes in output power there. Would you like to comment on what kind of power gain you got in January versus what kind of power gain you got in June?
You went down. You went down till we found that way of amplifying the effect. And then...
But my recollection is you were still seeing factors of 6 or 7 power gain.
we were changing the amount of power input.
Well, you can change the operating point, of course, but the issue is that the LANR we recognize it as a dynamical device, but the power gain of 14 in late January, power gains 6, 7, something like that in May and June.
But it wasn't as much input power. Take a look at it. What I think you had a phrase that I was taking very close care of these nanors, and in fact what I had to do was they become less robust, these did, become less robust in terms of the total amount of power drive I could put in. So we were changing not only the input voltages, but the total input powers. And you'll see that to maintain those levels of gain, we had to change those. You'll be able to see it over time.
Again, I guess I submit that this effect that you're referring to, which seems to, at the moment, to be such a big effect over one night, when you go over months, and if you include the change of operating point, in this particular case, you're losing something like a factor of 2 over something like 4 or 5 months.
For energy gain.
That's not bad.
Yeah, that's not bad.
We applied, Peter had an idea that we should try a different kind of protocol, increase the null space between, so we did that on a few. Here, for example, this run runs over, each of these counts is now 20 seconds. So this is about 8,000. So we got 160,000. This is over about 3 days. And what we see here, here's our aroma control. We're looking at input power and the delta T. This is not normalized, so we can't take the ratios. But we can see the impact for half of the amount or a third of the amount of input to the NANR. We're getting a much higher delta T compared to here. And the calorimeter is reversible. I mean, is time invariant, because here with the OMA control, we're getting the same numbers out over 3 days. And here's the delta T normalized, so now we can take the ratio, and that gives us a power gain. The heat flow matches it. As before, this is heat flow, input power normalized, so we can take the ratios. And here's the calorimetry, and we can see that to the, here's our control pulse, to the OMA control, we're not quite capturing all of the energy that we're putting in. Here we're putting in a fraction as much, we're getting much more out. And so here our energies match, and by being we're getting much more, here's our excess energy. And so it goes. And then we had a catastrophic event. Now normally I wouldn't show these, but this is really interesting because when we did, basically what happens is out of the NANR, we get a little burst. The shell gets a little hole in it. We get a cloud of nanometric material underneath. And what was most interesting was we had a loss of power gain down to 1. It became just like a resistor. Once we ended up having that burst, it came down, and I had to resheath it. So we have, and this was a complex thing. We're still learning about these. We had some unusual, unscheduled heat loss here and here. But the interesting thing was we go from getting a lot of brisk excess energy down to much less. Yeah.
So, Mitchell, on your unscheduled heat, if you go back to the last round of this and start out by looking at your temperature or your calorimetry. There's your power. If you like, you've got some what you might argue as being a lower level of this unscheduled heat.
Yes.
But now if you go to your heat flow equivalent, it's gone. And so the question is whether your unscheduled heat, namely, does your heat flow the same unscheduled heat in the vicinity of the catastrophic event or not? Namely, is that an artifact?
It's a darn good question. I'll tell you, when we do the input power normalized, when we don't put the input power in, it's a 0 in the denominator. So I've removed the data, and I have to look. It may actually be there. It's a darn good point. You've given me more homework. But basically what we find is when it's a 0, we get artificial numbers because of the tiny amount. So it may be there. I better look at it. Why do we use power normalization? We already talked about it. We do it so we can compare. We did this through February. I'll just run through a bit more. Here we're driving both the NANR and the control at the same time. It's not a really good way to do it. We showed, but I don't want to take too much time doing it. We're already running over. Here we're running up to the first week in February. This is delta T. Again, we can take the ratios. And you can see here we're reaching equilibrium, so we can do that. And here, again, we're putting less in, getting much more out. Here's our heat flow. Ran it up to May. We took it to a second location, so it even survived moving to the second location. Is this input power normal? No, it's just delta T, so we can't take the ratio. This is normalized, so we can take the ratio. Okay. Questions? Wait a second, I accidentally shut it off. So it would be a good time for questions till it comes back on. Yeah.
Would you say you've pretty much achieved repeatable science? Can this be accepted as repeatable science at this point?
Science is systematized knowledge, okay? That's always repeatable because we do the same thing. You mean, is it a repeatable phenomenon? I think it is. Though, to the degree that I showed you, it changes over time. I mean, it's not as perfect as a resistor. On the other hand, I could overdrive a resistor and burst it, and it won't be the same either. But I think within where people use to dismiss cold fusion by saying it's not reproducible, this is totally reproducible, within the limits that I say that it's changing. I'm going to just go through the next two very quickly, or at least this one. Before we get to Series 6, I did this side thing of making transistors with it. And I just want to show you, if you get your hands on these materials, be creative, because that's the way to find new things. And they're not all great, but what we did here is we made this complicated, overcomplicated way that we actually exceeded with the Series 6 nanors of using a second means to overdrive it. And what we did is what we call it is spillover, where we're creating a deuterium diffusion through a material. And so we do the normal loading, we do a secondary loading, and let's just jump ahead. And we looked at the impact of ultrasound. And the interesting thing is there's a gate voltage, and the important thing is we got excess energy. Here is our background, here's our remote control. We looked at the impact of ultrasound alone. We looked at the cold fusion transistor, which is the primitive nanomaterial. This nanomaterial is not even as advanced as what we put in the series 5 and 6 nanors, and we were getting energy power gains of 14. And this is a 2-drive level, so we were also seeing optimal operating points. And we were looking at near-infrared emission as well. And here's the control, ultrasound. The grid refers to the overdrive, which we use 3,000 volts to get it through here. And so we got not only excess power gain, but again we got the near infrared output, which might be thermal or non-thermal. We'll have to keep working on that to see which it is. Okay. We'll skip ultrasound. We'll just go to here. So what's the bottom line? Nanors. We do see excess heat in nanors. We've confirmed it by 3 different methods, including time integration. When I mean a one-dimensional nanor, I'm talking about a 2-terminal device. The current goes in one direction. The 2-dimensional nanors, we're having ultrasound come in from the other direction. And 3-dimensional is where we have the transistor. We have the gate voltage as well. We can skip this. The important results are the preloaded nanors, the series 5 and 6, have shown robust excess energy. One we showed here at MIT. I think that it's important because it's always been the goal to get excess energy, and I didn't get to do it in hot fusion, but we got to do it here. We've seen energy gains from 5 to 30. We actually went beyond this with the secondary activation, which we'll be reporting in a few months. I think although we've been criticized for it being low power, it was less than 50 milligrams. I mean, we're talking 35 milligrams of active material. So, yes.
So, Mitchell, you've been attacked again and again and again for having these things be running at such low power that people say we should just ignore them. I would like to point out from my own observation the rate at which you've made progress having moved to these low power systems is increased by a factor of 3 or 5 or something. So in a sense, your own work has benefited tremendously by this excursion to a lower power regime.
It's the time constant effect. It's the fact that instead of waiting for the calorimeter to take 5 hours to come back to ground, we can do it in under an hour. So I think you're totally right. It has evolved the system quicker.
Mitchell, that 35 milligrams, is that the weight of the powder?
That's the weight of the powder,
Okay.
not the weight of the nanor. Correct.
Wait, the powder, the palladium?
Yeah, the powder is much more than the palladium.
No, the entire powder is 35
Yes.
milligrams,
Including the zirconium.
including the zirconium.
Wow.
The palladium might only be a tenth of that.
That's right. Well, be a little more. I think that we were running it a little higher now. In the initial ones I showed you, Series 3, it was around 10%. And here it's probably closer to a third. Okay. Conclusion. I think they've got usefulness, even though people say it's low power, because I think we can bundle more. They enabled certainly me to do what was the second open demonstration here, and we ran this one instead of for a week for 3 months, maybe a little longer, and then we continued it, and in fact this one device is still active and producing data at this very moment for us that we'll be reporting, I hope, at ICCF 18. So today, I think we've got a clean, efficient energy production system. I think we've developed, by using the Nano Explorer, a team system that lets us examine different materials, different kinds of samples, additives, and be able to measure their activity by driving them at a number of levels so we can actually check out their optimal operating point manifolds and then know where to drive them. And tomorrow, I need you people to help us put them into artificial internal organs and propulsion and higher activity.
Mitchell, if I'm not mistaken, two folks from Kleiner Perkins came out late last year and he briefed them. And as I recall, they were skeptical that there was any effect whatsoever. And after an hour and 40 minutes of discussion, I think he succeeded in prevailing upon it that the effect might actually be a real effect. However, they concluded that there were no conceivable applications that could make anybody any money for, ever for this kind of technology. Do you have any thoughts on that conclusion?
How did the discussion go?
Go back to this. I mean, this won't be the first thing that people have laughed at
Well,
and been wrong about.
More concrete.
I mean, what do we use electricity for? Everything.
Well,
And if people had said that to the cat whisker, we wouldn't have had transistors. And if they had laughed at transistors, we wouldn't have had computers. And if they laughed at computers, we wouldn't have the internet.
much more concretely, this technology, even without electricity, namely the Kleiner Perkins folks were fixated on electricity production. However, suppose you had one of these systems running slightly above the boiling point, so you could use the heat directly to boil water. A significant fraction of the world's population at this point doesn't have access to clean water, and yet this technology, even without electricity conversion, seems to have an immediate application, which would seem to be a worthy one. Yet Kleiner Perkins didn't feel that way at the time, right?
I can't read what their exact reason was, but I think that we did not show the data of. I showed yesterday we didn't go above boiling with the aqueous systems because I didn't want to burn off $3,000 per liter material, not being Bill Gates myself, or having him in my pocket helping us. And here it's just a matter of it's early. We've only been running the nanors for a year, and only now are we going to above boiling levels. So when we get it, I think that you're absolutely right. The boiling water is the first application because potable water is the thing where we could help people immediately.
I wonder, do you think that Kleiner Perkins' assessment was the utility of a small-scale device, such as the nano, or the phenomenon being applied elsewhere in general at larger scale, that they concluded that it wasn't?
Actually, I need to back off of my over-enthusiastic discussion here. The folks for Kleiner Perkins, of course, are very good people, very sharp people. And the issue here is actually a different one. And the issue that's a different one is that over the years, people haven't thought that anything remotely like this was possible. And so the serious thought in terms of what to do if it's real, that hasn't happened on a very large scale yet. And if you like, the Kleiner Perkins folks did about as good as you would expect, having only a small time to respond to having been presented some amazing experimental results. So once you get your head around the possibility that this is an experimental claim here for controllable energy gain of more than a factor of 10, once you get your head around that, well, you wouldn't expect in the course of half an hour to be able to respond with something that's well thought out here. And so I apologize to pointing out the Kleiner Perkins and bringing them up and identifying them in particular in this, because the same issue has to do with many other folks when they're first exposed to the possibility that this actually might be real. The response isn't always. I mean, it takes time for thoughts to evolve as to what to do and how.
So
And this is
taking Kleiner Perkins out of the position of VCs or investors, but you're suggesting that they didn't have practical application for ZFX, or
the issue is that intellectually, the first step is to come to terms with there being an effect. And once you come to terms with this being an effect, then you need some time to acclimate yourself to understand what you might use the effect. For example, there are other folks who have taken the point of view that unless you could make a good fraction of a gigawatt electrical plant at a price, under 5 cents per kilowatt hour, that there's no application whatsoever. However, there are, we would expect there to be applications as well. The notion that maybe you could have small scale, localized power generation, which would be incredibly useful, is something that, if you like, hasn't been considered for a very long time by a lot of people.
It begs the question who these guys were. I mean, were they engineers?
Yeah.
Were they theoreticians? I mean, if you said Kleiner Perkins, but that means nothing to me. The question is, what is the quality of mind of these gentlemen? I think that your point is very well taken. That it takes some disciplined thought.
If you like, one of the Kleiner Perkins folks that came by is very well known as being one of the sharper guys on the block globally here. And if you like, what's interesting is that somebody who's as strong intellectually as that was not able in the course of 15 or 20 minutes to sort out all of the ramifications over a long time. It basically takes time to figure out what the applications are for this. And during a short meeting, there wasn't time to complete that cycle.
If Kleiner Perkins funds it, then the market in the VC community takes off. They validate very early entry markets.
Yeah.
The simple thing from my side in the valley, if you get a call and Kleiner Perkins is said to fund it, you just go. If you don't know the space, if you don't know the people, they have that much intellectual credibility in the VC community. Now, obviously, not a whole lot of things play out.
Right.
But
Now, Kleiner Perkins made it extremely clear that they would not fund this work under any condition.
One more thing. We have colloquia here. If you didn't sign up yesterday, sign up today with your email, and we'll make sure you're on the list.
And perhaps one last thing is that we, not knowing how things are going to play out, we scheduled the room for tomorrow, but no lectures were planned for tomorrow.
Just the exam.
And I don't actually think we're going to be having an exam. So mainly, I think the issue is that if there is a room and people want to use it, that the course itself is ending there.
Thank you for coming.